Inside a data center, the threats to critical power are entirely distinct. A high-energy arc fault behaves nothing like hydrogen gas accumulation, and neither resembles the chemical sequence of a battery cell entering thermal runaway. Protecting a facility requires securing 4 specific environments: medium and low voltage switchgear, VRLA battery strings, indoor lithium-ion UPS systems, and outdoor battery energy storage systems. Despite these differences, a common error persists, treating every localized alarm as an identical fire scenario and responding with a default facility-wide emergency power off, or EPO. This logic compares 2 distinct responses to a fault: the blunt force of the campus EPO on the left and the precision of selective isolation on the right. The EPO cascade creates the highest possible consequence. Activating it unnecessarily drops all independent powertrains, creating an immediate outage. Selective isolation works differently. By executing a supervised logic command in under 1/10 of a second, the system removes the specific hazard while preserving the healthy alternate path and the 700 kilowatt critical load. Treating all power anomalies identically creates avoidable common mode outages. Life safety requires classifying the specific hazard first, allowing for the isolation of the exact fault without dropping the entire building. This hazard and protection matrix is the foundational blueprint used to assign the correct detection and response architecture. It forces engineers to map a specific, credible failure mode to the earliest possible evidence of that failure. Only then does it define the safe action to take, followed finally by the appropriate suppression method. Because the physics vary, the suppression methods vary. Switchgear relies on clean agent overlays or sprinklers, while a lithium BESS installation demands a listed water density to control adjacent exposure.
Copying a single suppression concept across all power rooms ignores the chemistry of the hazard. Protection must be explicitly customized to the specific equipment and stored energy profile of the room. Looking at the hazard architecture for switchgear and UPS power conversion, the protection strategy focuses heavily on airflow and current. The primary threats in this environment are arc flashes, thermal faults at connection points, and cable insulation fires. The governing rule for this zone is that insulation failure must be detected before a sustained fire breaks out. This requires aspirating smoke detectors carefully mapped to the cooling airflow of the room. Operationally, the priority is to clear the electrical fault current first by tripping a breaker. The fire detection and suppression systems are there to address the residual heat left behind. Even after the current is cleared, human access is not immediately safe. The equipment retains massive amounts of stored DC energy in its capacitor banks. The delay required before entry is defined by the resistor-capacitor discharge rate. Dropping an initial voltage of 800 volts to a safe, verifiable 60-volt threshold often exceeds 11 minutes. Breakers eliminate the immediate electrical fault, but responders cannot bypass physics. Entry requires an evidence-based delay and strict absence of voltage proof. This cross-section of a VRLA battery room illustrates 2 distinct risks that must be managed independently: terminal heating and hydrogen gas generation. Hydrogen is highly buoyant. It rapidly rises to the ceiling, meaning detection sensors must be positioned at the highest level of the room, directly in the airflow and away from any dead architectural pockets. The control logic here is absolute. High-level hydrogen sensing must instantly interlock with the battery chargers, forcing a shutdown to stop gas production while simultaneously activating standby ventilation. The required exhaust capacity is calculated precisely based on the total number of series cells and the sum of the gas currents across all strings, determining exactly how much makeup air is required to dilute the hazard. Because hydrogen accumulation is the primary explosion risk, the safety mandate is direct. Charging must never be permitted if airflow fails. Ventilation is the primary fire prevention tool for lead-acid systems. The hazard architecture for an indoor lithium-ion UPS requires highly localized spatial monitoring directly at the cabinet level. Protection is separated into 3 layers: the internal rack monitoring voltage via the battery management system, off-gas detection units mounted at the top of the cabinet exhausts, and secondary room-level smoke detection. Off-gas detection serves as an abnormal state signal rather than a fire alarm.
This distinction prevents the system from misinterpreting a chemical precursor as an active flame. When a cell begins to vent gas, the system has an approximate 12-minute window to act before the chemistry enters full thermal escalation. This off-gas signal must be correlated directly with the internal rack BMS data to verify the anomaly before any contactors are commanded open to isolate the energy. Keeping off-gas logic separate from facility smoke logic prevents a localized battery anomaly from triggering a catastrophic facility-wide response. For outdoor energy storage systems, the worst-case scenario is unchecked thermal runaway, leading to flammable gas accumulation and ultimately deflagration. This architectural blueprint details the specific physical safeguards required to prevent a localized explosion from destroying adjacent equipment. Physical separation is the first defense. The installed gap between units must always meet or exceed the exact distances validated during UL 9540A fire testing. Here, a 1.2-meter gap provides a secure margin over the 0.9-meter test baseline. Inside the unit, gas detection sensors trigger action if flammable accumulation reaches 25% of the lower flammable limit, requiring immediate mechanical purging to prevent ignition. If ignition does occur, the system relies on a dual requirement. Explosion panels blow open to vent deflagration pressure, while listed water demands are applied externally to cool adjacent exposures. Every dimension, vent size, and sprinkler spacing must precisely match the unit's specific UL test evidence. Improvising purge exhausts spreads flammable gas unpredictably. Best survival relies entirely on exact physical compliance with tested containment parameters. This 3D cross-section illustrates an integrated whole-room protection model, fusing localized hazard data into one coherent view for the operator. The first layer is condition evidence. Utilizing EPMS data and intelligent relays, the system monitors thermal trends and voltage fluctuations, catching anomalies long before smoke is generated. The second layer is life safety evidence. Fire alarm control panels and smoke detectors evaluate actual combustion and off-gas signals, retaining distinct alarm classes based on the specific chemistry. The third layer is command and proof. Any selective trip, transfer, or suppression release must provide physical feedback to the operator, confirming the exact status of the hardware. This architecture must be tested against edge cases, including sensor time drift, faulty BMS mapping errors, and mechanical failures like a stuck ventilation damper. Safe escalation requires condition monitoring, life safety, and physical command functions to remain distinct but fully synchronized on a single auditable timeline. When a severe event does occur, operators rely on a strict incident playbook, like this 4-step sequence mapped for a BESS thermal runaway. Step 1 confirms the event across multiple sensors and establishes a wide exclusion zone. Step 2 isolates energy, stopping the charge remotely through authorized command. Isolation commands must never remove the specific auxiliary power required for deflagration venting or detection. Disabling these systems during a thermal event removes the active controls needed to prevent a container explosion. Step 3 controls exposure. Operators engage the approved water system, applying the exact listed demand, such as 12 liters per minute per square meter, to cool adjacent units, while carefully routing contaminated runoff into containment. Validating these systems during commissioning requires approved stimulus and simulation. Teams should never introduce live electrical faults or purposefully abuse cells to verify sensor logic. Finally, Step 4 governs recovery. Re-energization is never an automatic process. It requires OEM inspection, monitoring for extended reignition, and formal sign-off on the residual risk. Data center fire safety succeeds only when every warning, control, and suppression measure is assigned one explicit, isolated objective. By matching the response to the physics of the fault, engineers can neutralize the hazard while keeping the critical load alive.